My name is Akka. I work as part of the project Skills, and I'm part of PayPal. Okay, with me is Anil Gosel down here, and he will also talk a bit about all the good stuff that can be provided or you can get out of this project. But before we go down into that, I would just like to take certain use cases that we have been through and I felt is really relevant in the context of this conference, which is back pressure, right? So the application that we are dealing with is a crawler. The crawler is kind of unique. It's a batchy application, but it creates more content over time that you have to process. So your backlog is going to grow before it shrinks, right? We'll talk a little bit about the architecture, our selections of the technology, and then we'll go into the goodies that you can take away from this too. So, how does a crawler work? I mean, you can probably draw this diagram in 10 different ways. This is generally the requirements. You have got some crawl job. It has got, and this kind, although we can talk about crawlers in different angles, I'll just scope it down to a web crawler, just for the sake of simplicity here, all right? So, you have a crawl job, you have got some seed URL saying, here are the places I want you to crawl. Okay? Then that goes into a database, a persistent store. I think we used MongoDB for this. It could be HDFS, could be just about anything. Then we start the job. We stream these URLs out of the database, send it, okay, to the validation phase. Validation phase is checking, is that even a valid URL? Did the users provide us a bad URL, first of all? The second thing that you have to do is to check whether you just have crawled this URL recently and you don't have to crawl it again. So if we check and we figure out that, yes, let's go and figure out what that URL is, it goes through the download phase. The download phase is nothing but going off to the internet and then go to the URL that is specified, download the content. The processing phase after the download is is actually a two-step process. And as you can see in the detail later, it's a little more than 2 steps. So one side, you want the content, you want the pages to be sent to whatever big data system that you have so that you can analyze the content. The other part is it will have to look at all the links in the document that you have downloaded and send that back to be crawled again. So it goes back to the validate job, right? At the same time, you have to mark that I have just crawled this URL. So you plug that into a cache. This is a general view, how you really pull it through. There are 1,000 ways, 1 million ways, or infinite ways to do so. But there are a couple of problems here. So when you download one document, a document may have 10 links, and then you send those 10 links. So from 10, it can become 100, it can become 1,000. So the number of documents that you have to crawl is growing exponentially. You cannot crawl everything at once. You'll blow your system. So that diagram you just saw is invalid. We just cannot do that, right? We have to have concurrency, control over how many crawls can happen at any point in time across the whole rig. It's for internal purposes to control the network as well as external. We don't want to look at like a DDoS attack to anybody else, right? Then the resource usage. We want to use as little resources as possible, as little machines as possible to run this crawl. There are bursts. You can see that we have to buffer the URLs, and there are bursts internally that I'll talk about. And the other part is scalability. Yes, you cannot use one machine to do it. You have to be able to do it with the whole rig, right? So before we get into much of the solution, a little bit of the math, very rough math behind it. You can read most of it, so I'm not going to read through the lines, but you can see that the maximum number of URLs is a function of the initial, or basically the seed URLs, right? The links and to the power of the depth. So on the graph to the right, to the top right, you can also see, let me see whether my mouse works here. Okay, you can see that when you change the initial URLs, this growth is linear. The graph is actually a log-log graph. So it became back to linear, right? So if you have got 100 URLs to start with a depth of 5, outlinks of 5, this is average. You never know exactly, right? But we can collect statistics about that. You are talking about close to 1 million hits that you have to make out there. On the other hand, if only one seed URL you start with, but you are dealing with a depth, you follow the URLs 10 levels deep, you are talking about 10 million URLs. So it's a 1 to 10 million expansion. I stole this slide, so I feel everybody knows about that already. I don't have to talk about it. Really, just to refer back to what we are dealing with and why, let me just skip to the next slide right away and say, why does the Reactive Manifesto matter? As a crawler, there is definitely a time window that we have to execute, right? With that time window, we have to stay in that time. So it has to be responsive, not to a request level, not to a fine-grained level. So the responsiveness comes in at a very coarse-grained level. Resiliency is, however, very important because now you have external systems that you don't control as part of your dependencies, right? We have to make sure that the system stays up, no matter what you are crawling, no matter what kind of job is given to you, whether that URL, that link even exists in real world. We have to stay responsive, resilient, right? So I just talked responsive. Basically, it has to keep working, and there are cases where when you crawl, you get a URL, but you don't know whether you are going to download a 2K document or a 5 meg document. You don't know whether that link goes across the ocean or not from the link itself. So what's going on? Some of the URLs might take very short, a second, to get the results. Some others might take 10 seconds, right? And of course, in order to make all this work seamlessly, we have got this message-driven architecture that supports it from the bottom. Let's look at the ingredients right away and how we put the systems together. First of all, we need this humongous buffer that buffers all the outlinks and then keep crawling it. So Kafka kind of provides that buffer, right? It also provides the horizontal scalability. So basically, you can have n number of nodes scaling up and down based on your needs, right? That would keep pulling the URLs to crawl from Kafka. Okay. Akka Streams. The nice thing about Akka Streams is really that it's highly efficient, highly performant, and it has this end-to-end back pressure. So you might ask, why do I still need back pressure? I've got Kafka already. Yeah, I'm downloading from Kafka or pulling from Kafka whenever I need. But internally, you don't know some of these resources that you are crawling takes very long. Some of them takes very short. You might have a bunch of very long URLs that you have to download at any point in time, right? So we need something that makes sure we don't overload the system. Next part is async client. So with an async system in the middle, we would need an async client that doesn't use up threads, that is non-blocking. Okay, and we combine that using a nice operation that was provided in Akka Streams called map async unordered, which is basically saying execute. I only control that you can do, clients can do 1,000 connections, but whichever connection comes back first will go to the process first. It doesn't have to wait for any ordering. All right. So that gives us kind of the ingredients. Now, next slide we put it together and see how it looks like. So in this case, we have got the crawl job, right, that puts into JobDB. Actually, the part from JobDB into Kafka is also a stream. I'm not focusing on that, but it does some very rudimentary transformations depending on the job type and so forth. Then it sticks the jobs, let's say 100 URLs. In real world, we are talking about millions. Okay, just to let you know the scale. So let's say 100 URLs, it sticks it into Kafka. That goes through the steps that I have described before, the validation steps, the download steps, the process steps. Now, what's different this time is the outlink URLs, the links that you parse out of the document, go back to Kafka. And although I show like 2 pillars here of Kafka, it's actually the same instance. Just for ease of comprehension, I'm just showing it as 2 pillars. So the URLs actually circle back to the validate job. At the same time, we update a centralized cache that says, I have crawled this URL at a certain point in time, and this is my TTL. This is my timeout. If I hit the same URL again within that time, then I'm not going to crawl it again. I'm just going to use the old results and link it together. So finally, each of these documents that we download gets a little processed with some metadata and pushed out to our big data system, which is actually a Spark at this point. Okay. So why Akka Streams? I think that's probably one of the key messages here. Is definitely the pure async processing that complies and that works with the async I/O that we are using. Okay. Yet the other part that is really, really appealing is the programming model. And that's when let me just talk about my experience. I had to deal with a lot of code, looking at a lot of code that is not my code, and it's always a headache. Okay, so the issue at looking code is people used to code very deep nested functions. You have got one function calling 5 other functions, each of these functions calling another 5 functions to make sense of what that code does. You have to kind of track down and figure out down below. And the abstractions are not always very clear. Of course, our APIs, the APIs that are designed from open source, they tend to be clear to what they're doing. Even though sometimes you really want to understand the behavior down below, you have to go in, right? So with that, let's take a look at how the stream looks like in detail. So let me just go over the stream, and I'll talk about the abstraction a little bit at the end. First, we have got this source. It's a prioritized source, which means that it reads from multiple Kafka topics. How you do prioritized source, I'm not going to talk about. You can look it up in the Streams cookbook. Okay, that will then move to the crawl job. The crawl is actually the download here. It basically goes off, picks an async client, an instance, and then goes off and says, go download that URL for me. As a result of it, you may have a good result as an outcome, a tag saying, I've reached the max pages by one or another criteria, and it just says, don't go forward. The other one is, it looks like I couldn't reach that resource. Let's retry, okay? Or goes into the retry category. So the easy part to really explain is the good part, right? Basically, you parse it. You have got 2 processes running in parallel through a broadcast that says, I want to process the data a little bit. Basically, we leave most of the processing in a big data system behind us. We take the outlinks, right? And then send it, pass the outlinks out of documents, send it back to the outlink sink. That outlink sink actually circles back to the source, right? We save the data as raw data in HDFS. I think we are not doing that anymore as I speak today, but this is a couple of weeks old, right? Then there is a graph database. So we try to send out a topology saying document A links to document B, C, and D, and D links to E, F, G, right? So that creates kind of a graph structure. And that goes all into the graph sink, which then connects to a graph database in the back. So the next part is max page reach is simple. Just cut it off, stop the graph, and I'm done with that part of the graph. It's a leaf node. The retry case is a little bit different. So there are some cases where we say, OK, I couldn't even find that DNS address. I couldn't find the site that we are talking about. So what does it mean? Should I even retry? So we say, no, it failed. Don't go to retry, right? So that also stops off the graph. The other use case is I got a 503 out of a call, out of a download. That means that that server might not be ready. In that case, I would say, well, let's wait for an hour and go back. So that goes to the error sink. The error sink actually circles back to a source topic. I'm sorry, I went too far. So now, the nice thing about Akka Streams that I really appreciate when I look at code is I look at this code down below, which is the DSL. I can figure out right away what the whole thing is doing. I might want to drill into what crawler flow does down here. I might want to check what the outlinks flow and data sync flow does. But those are pretty shallow stacks by themselves, right? So you can see that it's actually a one-to-one mapping. These lines that go off, you can see that those are one of the broadcasts. This is like the broadcast 0 in this case, another broadcast, a broadcast for the retry, and so forth. But all of a sudden, you start to figure out, hey, this is how the whole flow is supposed to work. What we get out of it is a very efficient system, very low thread count. This thread count is actually controlled by Akka. Right, by the parallelism factor in Akka, the min parallelism, and so forth. Right, and this is more of a batchy workload. And then using a HTTP client, pure async HTTP client that doesn't use threads, doesn't cost us to have the parallelism on the internet. And let me just step back one step and say this is not the first generation of the crawler. The previous generation was one thread per synchronous request. So you can imagine how many threads there have to be in order to support this amount of crawling. So the other part is the high latency URLs. And there could be a multiple of the low latency URLs in terms of download, access, download, processing. Right? That basically won't hold back the slower ones. So whatever is fast will go through it. Really fast. So if we say we have a parallelism of 1,000, this is per virtual machine, we are saying that these 1,000 connections are going to be used at all times. Resiliency, right? Basically, we will not process what we cannot process. You'll see in the next slide in just a moment how that looks like. And whatever we cannot process and we have to persist for some longer time, that goes into Kafka. The outlink URLs, they circle back from one side, basically saying, I produced 5 links out of this document. They come back into the other side and pile up in Kafka. Yes, you have to configure Kafka correctly to make it work. But I don't think that's a big problem for Kafka. OK. The other part is the pull model plus the push-pull model of Akka Streams. Well, Kafka is still a pull model. You basically download a batch at a time, and then you start processing it, right? But that gives us kind of the resiliency, the scale that we want, and the distribution of the workload using Kafka itself. All right. So here is basically just a small job running off of a single VM. I started this with 100 seed URLs with a parallelism of 1,000, which is a common number that we use, okay, with a processing time that we figured out roughly between 1 to 5 seconds and between 0 and 10 links per document, right? Only 100 URLs, totally assuming that there is no duplicate, there is nothing in the cache. What we'll get is we'll have to crawl about 300,000 documents. However, it's not all at once. It's not piling up at once. You can see in the graph that as we go, we will increase slower and slower up until it came to a plateau. So for this 100 seed URLs, we have got a queue size, or basically a backlog, let me call it a backlog, of about a little bit over 100,000 at about 200 seconds into the crawl. Okay, this is a very small crawl job. We are, in real world, we are talking about a big cluster and doing about millions of seed URLs at a time. All right? Then, well, after it stops growing, after we have exhausted all the outlinks up to the depth that we wanted, you can see that it starts chewing down and processing things down linearly. So the queue now becomes a linear function of time, right, from this point on, which is around 350 seconds into the crawl. The notable thing, though, is this is the processing of our system. Okay, so you can see that the system stays flat. There's some up and down just a little bit, but it stays flat and resilient and stable throughout the whole run, right? There's no big spikes. There's no big dips. So that's pretty much explaining the crawler and why we are using such technology to basically have only, I think the current configuration is a 4-core system, 8 threads each, right, to run the whole thing. Extremely efficient. Now, I think I'm pretty much done with the crawler, but let me just get out of this topic and say, what are the challenges? So my job is really working with developers. We are part of the infrastructure team, and we work with developers to use the technology. So when I say crawler, it's actually a team that is not my own, that will run and own that code. And bringing them up to speed to the right technology to solve their problem has been quite a challenge, right? So the first round of code that we asked people to do, explaining everything to them, they started coming up with some deeply, deeply nested functions. And the streams are not connecting. They have got one stream reading out, another stream reading in, having an actor in the middle. I said, no, that doesn't work. That doesn't work. You don't get the back pressure unless you implement your own back pressure protocol. Okay. And soon enough, they had buffer overflows and all kinds of problems. So we have to go in and actually work with them hand in hand to come up with code that looks as simple as what you saw in the previous slide, right? But it is a mindset change from a very deep nested functional architecture or method-based. These are Java programmers that have been doing Java for 10 years or more, right? And getting them to change that to see things like this is the flow. Each component does a little thing, and then it hands off to the next part of the flow. Took more than I thought. The second challenge is, of course, the maturity of the infrastructure. So this code in production is still on Kafka 08. So this is a little rant to Kafka. I hope they fixed it. I've heard they fixed it, by the way. Kafka 09 has got this fetch as a heartbeat kind of architecture where basically you say if you don't go back and fetch data in a bound time, then it will say, oops, I think I lost you, and it says I'm rebalancing the cluster. When you rebalance the cluster, Kafka goes away a little bit, right? So it freezes. It's almost like a big garbage collection in a sense. So we don't want that to happen. And we tried to make it work with 09. We couldn't do the upgrade, and we are in the process of upgrading to 010. And as far as I know, 010 has a solve from the Akka Streams Kafka side, and 010.1 has got a final solve for that. Hopefully, we haven't tested it out, so this is work in progress to do the upgrade. All right. So what would it have been? That's the question. If we didn't jump in and say, hey, let's get it right, let's get it efficient, right? I see a lot of code that is shoehorned together, concurrency that people wrote by themselves, their own thread pool, their own way of doing logs, and as we know, that doesn't fly very well. People, especially the people that do the business logic, they are not very good at doing the concurrency or dealing with logs. And when it passes down from the first generation to the second generation, especially then, it's going to get wrong. People leave the company, people leave the team, new people come in, they look at it, they don't totally understand why you put that log there, right? Why did you say this has to be volatile? Why is it atomic over here and over there? So that's an interesting point. And then it would have been something that nobody could understand. Whereas at this point, you read the code, it takes probably no more than about 5 minutes reading through 2 files out of the whole projects, and you would understand the code pretty much end to end, right? The processing pipeline wouldn't be visible, wouldn't even be thought out. You think anybody is going to write a DSL, especially if they write it in Java? Java is not very good at that, right? To explain the whole flow, let's say. So we'll end up with clumsy code, hard to manage. But there's another challenge to it. The last point is really the training cost. When we approach people and say, guys, this is the right technology, say, oh, we are not used to this at all. It's a very different way of thinking. So they are kind of taking 3 steps back already, right? And managers that have to manage teams that do multiple projects will say, but I want the technology for all my projects to be the same. I want my team to be coherent. So it takes quite a bit of convincing and trying to make them understand that, hey, this opens a new perspective for your team. I'm not saying you should leave what you are doing, but it should be that the team chooses the tool, the right tool for the right problem. There are problems that are to be solved with tools like Java EE Spring. There are other problems that are to be solved with Golang, I think this is a right problem for this tool here that we have. So yes, it took quite a while to convince people, and that is also getting a bit against the adoption curve. All right. What did we get out of it, bottom line? We had this old thread-based Java architecture, and then compared to moving to the reactive architecture with Kafka, with streams, and with async I/O. Okay, we are talking about, of course, the thread savings is much more than 90%. The savings on the performance and on the rig is about 90%. Okay, so that gives us a clear idea that the infrastructure cost is going to be much less as we go. All right. The next part, we are just going to talk a little bit about all the goodies. So you heard about what we did already. Now I'll ask Anil to come up and talk to you about what you can take away from this, the bits and pieces that might be useful for you. All right, Anil, thank you.
You can hear me well. So Akka has talked about high efficiency, resiliency, and dealing with the bursts with Kafka, all that stuff. So I'm going to be talking about some of the Akka Streams related utilities that we've developed while working on the Crawler project, as well as a few other Akka Streams projects internally at PayPal. But before that, I'm going to be touching on the Skips project a little bit. So when you're developing microservices, if you have one, maybe not a big problem, but when you have an ecosystem where you have like tens of services running together, the consistency becomes quite important. Whether it's monitoring or logging, you need to have a consistent way of collecting the metrics, or if it's an HTTP REST request, like going through the ecosystem, and if your services are communicating each other, you somehow need to be able to correlate the logs, and sometimes you might even need to have some uniformity in the logs. You might need to log certain things in certain phases of a request, etc., which might be allowing you some reporting and tooling related stuff later on. Similarly for security, you are as strong as the weakest point of your weakest service, basically. You need to be able to, for instance, like for SSL context, you need to be able to initialize that in a standard way across the company. And while doing that, you might have some guidelines saying that, okay, this is how it should be done, etc., and ask all the developers to follow that and then make sure that they do that. But that's going to be a little bit error-prone, and as well it's going to be quite inefficient. So that's where the Scoops project basically helps a lot. But before going on deeper on Scoops, so it's not a framework itself. When you code your business logic, etc., you're just using the Akka API. So that's the important part for us. Like you are coding against Akka. And we have quite many projects out there on the GitHub repository you can check. You don't have to pick everything. You can just pick and choose. For most of the projects, all you need is an actor system provided. Of course, there are a few of the artifacts that has dependencies in between, but we try to keep them as minimal as possible. For most of the projects, you just need to give an actor system. So what Scoops provides is, at the core of it is a very lightweight bootstrap module that we call it Unicomplex. What it does is basically starts up the actor system, the Akka actor system, and it also defines some lifecycle events like starting up, active, shutting down, etc. So what it allows us is any actor in the system basically can register to receive such lifecycle change, state change events, basically. So what it allows us doing is that to be able to like register some hooks in the application during a startup, like some initialization or some cleanup stuff during the shutting down of the system. In a similar fashion, for instance, for Akka HTTP, if you're developing an Akka HTTP application, if you have many routes, usually you do bind and handle, and when you do bind and handle, you basically pass the entire routes, etc., right? So Scoops tries to provide some integration hooks via configuration, where it allows you to define, for instance, a bidirectional Akka Streams flow to be prepended in front of a route. Like you can do it as a default one for each of the routes, or with a configuration you can like configure it to be just only for certain routes, etc. So another thing that Scoops provides is the loosely coupled module system that we call cubes. It's nothing but just a jar with some configuration. Like in the configuration, you specify your routes and you specify which actors needs to be initialized at the startup, etc. So what it provides is that a cube. Oops. How do I get rid of that?
That screen? I'll get this guy out.
Yep.
Okay, now let's see.
Just click on
it's
it.
down here, right?
I think the hotel internet is, the wireless is not playing. Anyway, so the cube is basically has a dependency on the bootstrap module, the Unicomplex, and you specify your routes and the actors that you would like to be initializing during startup. So what it allows you is that you can all do java-jar and run, and the cube will be able to basically run by itself. So the good thing is when you have two modules basically and bring them together to the same class path, it's going to be just one JVM. And when you do java-jar, it will be just one JVM and one actor system. You'll be basically be getting all the optimizations of Akka. So you probably read quite many articles out there about microservices. Everyone is talking about how big it should be. Is it too small, too big, etc. I mean, another important aspect is that you should be able to, whether it is too large or too big, you should be able to evolve your services going forward. You should be able to refactor. So what the module system provides over here is that if time comes in, I can easily take my application, if I build it in terms of like proper modules, I can just separate them out and run them. I just need to separate them and take it from the build.spt and run it by itself, and all of a sudden you get two services running. And the other thing that the module system allows is that in Akka HTTP, you need to append all the routes together, concatenate them, and pass it to the bind and handle. With the configuration, we can basically allow the some of the routes to be defined in a jar. So, for instance, for Scoops, we have a project called Scoops Admin Console, which shows a JSON representation of all the JMX pins in the JVM. So, a Scoops application, to be able to get that endpoint, which is /ADM, all the team needs to do is drop a dependency in build.spt without making any code change in the application. By just dropping a dependency, you all of a sudden get a utility, an endpoint. So it provides an HTTP client, which is on top of Spray. I mean, on the server side, we already upgraded to Akka HTTP, and we are on the process of starting upgrading to Akka HTTP on the client side as well. It provides an HTTP client on top of Spray, which provides some hook points and pluggable endpoint resolvers as well to be able to register different service discovery mechanisms as a chain. You can just specify a logical service name like payment serve, and then with the service discovery mechanism, it will be able to, whatever you register for your own company, whatever you use, it will be able to resolve it to the actual address. And also like a request and response filtering chain for the HTTP client as well, which out of the box we don't get with Spray or Akka HTTP. Scoops provides quite a bit of tools, testing tools and interfaces to make it a lot easier to during unit testing especially. I mean, the project itself is mostly written in Scala, but as Akka does, we have, for any API we provide, any extra API utility we provide, we have Java APIs as well. And we have activator templates for both languages, and they are already configured with Docker, so all you need to do is run spt docker and just Docker run, and you can just deploy it today to AWS or wherever you want. It's basically production ready. So we have quite many of goodies that Akka mentioned, so let's talk about a few Akka Streams specific utilities that we've developed while working on the crawler project and a few other projects in the company. So one of them is Perpetual Stream. So when we were working with the crawler team, so what we have requested is that, hey, I do not want the stream. So in Akka Streams, basically, it has a great feature where you first define the blueprint of your stream, and then you run it. And you can materialize it multiple times, of course. But you first create the blueprint and then run it. So what they came up with the request is that, hey, we do not want the stream to start until some certain parts of the application are like already initialized and all that stuff. We don't want to lose messages around that, and we don't want to cause some abrupt failures around that. We want everything to be ready before we start the stream. So Perpetual Stream basically is a trait that helps with that. I think I'm having the same problem again. Perpetual Stream basically helps with that. It registers itself to receive lifecycle change events by the Bootstrap module. And anytime system state changes from starting to active, etc., Perpetual Stream retrieves those events, those messages. And actually, you define your stream, right, as nothing special, just like an Akka stream. Nothing. But you just need to override one function over there and assign your stream to that. So it is Perpetual Stream's responsibility to call the run on the on the stream actually. So it waits a signal from Unicomplex to give a thumbs up. Hey, the system state is active, and only then it basically runs the stream. Similarly, during shutdown, you may want to do some graceful shutdown of the stream instead of like all of a sudden like things are going south. So it again gets the shutting down signal, and by using Akka kill switch, it it gracefully shuts down the stream, basically. And it also like provides the implementers to register some shutdown hooks for cleaning some other stuff, etc. So another one is persistent buffer. It's an Akka Streams stage, a custom Akka Streams stage that we developed. So it is basically a buffer stage that writes to memory mapped files. Like it's backed by canonical queues. The idea is that it basically decouples the upstream and downstream. So it doesn't back pressure anymore. So if downstream is kind of like having trouble, right, or not available, and if you do not have the option of back pressuring, or if you cannot deny the incoming traffic, for instance, like in case of a beacon or something like that, and you don't want to lose the messages, it basically writes to the disk. And when the downstream comes back, it continues where it left off. Or the other scenario is that if the stream basically fails, right, or restarts, or JVM restarts, etc., it can basically like able to continue where it left off. I mean, one common scenario that we have that was if for the Kafka producer, like if Kafka is rebalancing, etc., in those scenarios, it became quite handy. It also has an optional commit stage. So it basically like you can detach the index updating of the canonical queue to a different stage. So what it basically helps is, normally Akka Streams is at most once delivery. So with the optional commit stage, now between the persistent buffer stage and the commit stage, you will be able to get at least once delivery semantics. That's what it basically helps with. And we have a different version, another version of the persistent buffer, which is called broadcast buffer. So it's pretty much the same. So persistent buffer is one in, one out. Broadcast buffer is one in and it's fan out. Basically, all the outgoing downstream branches will be independent and going on their own pace, basically. So, I mean, in summary, Akka has talked quite a bit about that. If you would like to build highly efficient, resilient, and if you would like to be able to deal with high bursts, the combination of Akka Streams, Kafka, and async I/O seems to be a great combination. So Kafka helps a lot with dealing with the burst and buffering those, and Akka Streams, especially with the back pressure, helps us like keeping the system under control. Basically, it prevents it to be overloaded and keeps everything sane. And very importantly, it makes it really clear to visualize what the application is doing. Like there might be too many things going on, but I mean, in just one glance, you can just get the overall idea about the application by just looking at the graph DSL especially. And most of the times, it basically ends up like doing a whiteboard drawing of the application, and then you pretty much put into the code pretty much that whiteboard project. So that helps a lot. And when you have quite many microservices in your ecosystem, consistency and standardization gets quite important. So Scoops might help with that a lot. Check it out. And like the utilities that I've just discussed about Perpetual Stream and persistent buffer, take a look at those as well. So we are on GitHub, github.com/PayPal/Scoops. There's a Gitter chat link over there. I mean, we would love to get some feedback, whether positive, negative, any kind of feedback. We really appreciate that. Click on the chat and share your opinions over there. You can follow us on Twitter with @Scoops. And we also have a booth out there, so if you want to come talk to us, that'll be great. So, thank you. Yep, any questions?
The workers, you mean? Yeah. Somewhat. I mean, there are some other influences. in the crawler, which, as I said, is you never know what that document is, how big it will be, how many links it will have, right? So that is one part that is out of control of Kafka. We download a chunk of Kafka, but internally, we have to make sure that we don't get ahead of ourselves, right? That's where the back pressure comes in very handy. All right? Other questions?
Could you talk a little bit about the monitoring piece, JMX piece?
Absolutely, absolutely. You want to take it?
Go
Oh, okay. So this is another piece that we kind of thought we use a lot of JMX internally. So a lot of what we're doing in the system state, Anil talked about the cube structure, the routes that we compose, and also even down to which mailbox is, which Akka mailbox is not in good shape and so forth. So we built a lot of these tools into Skills to either directly export such stats, request stats, for instance, or on the other hand, it attaches somehow into the Akka system and tries to figure out your mailbox size. Okay, so, and it exposes that as JMX beans. Now, the JMX consoles that you find around here are not very good, and also using RMI with JMX is deadly. Don't do it, right? So we were thinking about how to expose all this information. And JSON, especially pre-printed JSON, seems to be an easy way for people to use and for machines to consume. So let's say if you want to build your own whatever monitoring tool that monitors 10 services or 10 nodes, right, you could just go and grab that JSON. But if you want to monitor it by eye, it's actually easier to watch than if you go through a JMX console, for instance. So a lot of these stats are exported from the system. And if you want the console is based on our module system. It's one of the modules. So all you have to do is you drop that module in. The bootstrapper will wire it together into the main route. Okay, if you are familiar with how Spray routes or HTTP routes work. And then as you go to /console, it will bring you to a link of all the JMX beans without ever going out of the JVM.
And quick addition to that is, I mean, most of the time before you even start your Akka application in your company, probably you already have a monitoring solution which you might need to integrate. And with such scenarios, especially with the hook points, Scoops makes it a lot easier to registers and then integrate with those.
Thanks. Any other questions? All right. In that case, thank you very much.
Thank you.